Hello again everyone, welcome back to ptet.chemistry channel. So in this video I will cover electrophilic addition mechanism. So we associate electrophilic addition mechanism with things like unsaturated hydrocarbons. So we talk about unsaturated hydrocarbons being those that contain carbon-carbon double bond. But in actuality, it also includes carbon-carbon triple bond as well. Although in most A-level syllabus, including the Cambridge International or other major UK examination body, they don't really cover a lot of those carbon-carbon triple bond chemistry. So we'll focus on the one that involve the carbon-carbon double bond during electrophilic addition. Okay, first of all, addition refers to two or more reacting molecules come together. Well, when I say come together, they join together. Perhaps those are better words, yeah? So two or more reacting molecules that join together. So that's the idea of addition. So you ended up with lesser number of molecules than what you started with, because you combine, you join two or more reacting molecules together. Typically, this just involves two reacting molecules. Those are very simple cases, yeah? But in general, addition just means you add together, you combine together, you join together reacting molecules, okay? Electrophilic. So in the other video, I cover something called free radical substitution, where we talk about homolytic fission. Here, we will talk about heterolytic fission, which is the case with most organic chemistry mechanism in A-level, because heterolytic hetero refer to unequal. Why is it unequal? Because in a covalent bond, you have two electrons, right? So in a covalent bond, you have two electrons. So I'll give you an example, such as X and Y. So this is a covalent bond. In this covalent bond, there are two electrons because it's just one covalent bond, okay? So I've deliberately chosen XY here rather than showing XX or YY. That means these two atoms have very different electronegativity, let's say, okay? I'm not telling you the identity of them. I'm just being random. I'll just put this delta minus, and this will be delta plus. Okay, so this bond is polar. So I can break this bond in the sense that I can have two electrons flowing from the, bond. Okay, not from the atom, from the bond, because the electrons from the covalent bond go to the more electronegative element because I'm breaking it. This has more electronegativity, meaning to say the definition of electronegativity from your AS or whatever level you're doing is basically the ability of an atom to attract that bonding pair of electrons towards itself, right? So it makes sense that when you break this covalent bond, the electrons will actually go there. But we're doing heterolytic fission. That's why we are using full headed arrow. The electrons come from the covalent bond. Both of them go to this atom. So meaning to say you will get ion, because we are talking about movement of two electrons. We will get X plus Y minus. And Y minus will have a lone pair because the two electrons in the covalent bond go to Y. I hope that makes sense now, okay? So in that sense also, you can think about the opposite. When you have that, which has a lone pair of electrons, okay? It has at least a lone pair of electrons and is electron rich. That is what we call a nucleophile, okay? Must have lone pair. That's why like every reactions that involve heterolytic fission, you must show the nucleophile having lone pair. Must have lone pair. What have I written down? Must have lone pair of electrons, okay? It can be negatively charged, but it doesn't need to be, okay? So the definition of a nucleophile is a species which is electron rich. So electron rich, meaning to say rich in electrons, okay? It must have a lone pair of electrons on itself, not necessarily charged, which means can be charged. So these are the kind of things that can trick you in the MCQ, yeah? They say, which statement is correct? They say a nucleophile is negatively charged. It can be charged, but it's not necessary. Because if I tell you some examples, things will include like NH3 is also a nucleophile, H2O apparently is also nucleophilic, but not very good nucleophile. On the other hand, things like H plus would be the electrophile because it is electron deficient. It's the opposite of electron rich is electron deficient, or you can say poor in electrons. Must have empty orbital. Must have empty orbitals. Okay, so that means you must have empty orbitals for the electrons from the nucleophile to attack. I've given it away already. That's actually the next point I was going to cover. Okay, can be positively charged. Okay, so that one can be negatively charged. So I say again, emphasize on can be, all right, because there are electrophiles that are not positively charged, and I'll show you an example. Example, BH3. You don't normally see this in organic chemistry, but I'll show you that you learn this in inorganic chemistry. Okay, electrophiles. What else? Well, I don't know. I mean, typically we associate with like I don't know, like primary halogenal alkane, etc., etc. Okay, or even carbonyl of ketone or aldehyde, which I'm sure you have covered. Okay, so when you have that BH3 and NH3, I hope you can see that the NH3 can donate the lone pair to the BH3. Okay, we show that the dative covalent bond because that is the electron pair donor. That is the electron pair acceptor. That thing there shows both the electron and the covalent bond come from this. We do not, I mean, you know this as a nucleophile usually. You don't normally know this as electrophile, but I'm just giving you an example of an inorganic reaction. Inorganic meaning not organic. Okay, usually you typically associate with carbon, right? But this is an example, perfect example of a nucleophile attacking an electrophile based on the definitions. Yeah. So BH3, as you know it, is it's just like BF3, which is actually in your shape of molecule. So that is got an empty orbital. So that is empty because that is trigonal planar. So it's only sp2 hybridized. It's got an empty p orbitals. They can accept the lone pair from the NH3. What do you become now? Well, now you become tetrahedral because of that dative covalent bond. Now you form this, which is tetrahedral, and it become 109 degree. So that is now 109 degree. That is now 109 degree. Okay, anyway, this video is supposed to be about electrophilic addition, so I should really get on with it. Okay, so what do we know? We talk about addition across alkene, right? So let me start with the simplest alkene of all, because there's no point of starting with complicated idea. So this is C2H4, this is ethene. It's a gas at room temperature and pressure, yeah? So it's not easy to handle because it's a gas at room temperature and pressure, alright? So it's not like a solution or liquid that you can pour out. No, it's not. It's a gas at room temperature and pressure. Alright? What happens when you have bromine close to it? If you can bubble the gas into aqueous bromine, you will see decolorization because you will get addition reaction. That is your O level. In A level, you have to write mechanism. Okay, including in AS and A2. This carbon-carbon double bond is rich in pi electrons. What are the pi electrons we're talking about? When you have an alkene, this is the three-dimensional shape of an alkene, where I can show the p orbital overlap sideways. So that is your pi bond. Your pi bond is weaker than your sigma bond. The pi bond electrons are the one lingering around on top and below the alkene plane. So it's trigonal planar, it's actually planar. So you actually have that cloud of electrons. That is your pi electrons. Okay, so it is the pi bond that is rich in electrons that can polarize the Br2 molecule, which is non-polar. But when this come close to this is rich in electrons that can polarize the bromine molecule. This is rich in electrons. Electrons are negatively charged. So if it want to polarize this, it will not make this negative. It will polarize it in such a way that this is becoming delta positive because it wants to be attracted to it. Electrons in the pi bond are negatively charged. It will polarize this to become delta plus, which means the other one must become delta minus. Alright? But then, I talked about heterolytic fission just now. So we are not thinking the bond will break straight away. No. it has to be started by something, okay? In an organic reactions, we always have this general, I say general because it is general saying, that the rich in electron attacks the poor in electron. The rich in electron attack the poor in electrons. So that is the mantra, yeah? Okay, so that means your arrow which shows direction, yeah, must go from rich in electron to poor in electron. It's not both-headed, it's not double-headed, it's single-headed. The rich in electron is not the carbon, it's the pi bond. It's the pi bond which contains the pi electrons. That is the one that's rich in electron. That is your nucleophile. The carbon-carbon double bond is the nucleophile because the pi bond, which is the pi electron, is the one rich in electron. It's the one that polarizes the bromine molecule such that this side becomes delta plus. And this is the one that induced the attack from the rich in electron to the poor in electron. Once you do that, then you do the heterolytic fission. You break it. Does it matter I draw it on the other side? Not really. You can draw on this side as well. It just look a bit neater, yeah? So what happened then? This is a very simple example. So it's actually very, very simple. You add a bromine. This is a double bond. Now you already use it for attacking this. You use the pi electrons, the pi bond. Therefore, you no longer have the pi bond. If you no longer have the pi bond, then the carbon can form 4 bonds, right? 1, 2, 3, 4, because you pick up a bromine. Does it matter whether the bromine goes here or here? We will discuss about that now. But look at this carbon. Okay, this carbon is now 1, 2, 3. Do I have another hydrogen? Not really. I started with 2 hydrogen. Do I have another bromine? But I haven't. The other product is this, you see? The other product is this one with a lone pair. You give both the electron to the bromine, just like this. This one leave. They are broken. This is fission, totally broken. Lytic, breaking, splitting, totally split. Now you get this species which got a negative charge with a lone pair. Now you have the bromide with a negative charge with a lone pair. So that has left the molecule, so it's not there. So this carbon is simply what we call a carbocation. It has a positive charge because this carbon has added something, but this carbon hasn't added anything yet. Overall, you have 2 species. This is +1, this is -1. +1 and -1 give you 0 net charge on the right hand side. No charge, no charge. These are dipoles. These are not proper charge of ions, yeah? No charge on the left hand side. So these are balanced equation in terms of atoms, in terms of charges. Alright, this is what we call a carbocation intermediate. Very important to label it. Carbocation intermediate. Is an intermediate. Okay, it's not a transition state, it's an intermediate. Cation, positive charge. Carbocation, positive charge on the carbon. This is what we call a primary carbocation. I like to write 1 degree, that stands for primary, or you can write the word primary. The carbon with the positive charge is bonded to one other carbon. These are hydrogen, right? The carbon with the positive charge is bonded to one other carbon. It's primary carbocation. Alright? Now, how do I form the product? The charge is on the carbon. The charge is on the carbon, yeah? From the lone pair, because this is the rich in electron, not the negative charge, but the lone pair on the nucleophile, attack the carbon. Not the negative attack the positive. No. Rich in electron is your nucleophile from the lone pair. Poor in electron is the atom, which is electron deficient. Okay, the carbon with the positive charge, it attacks that carbon. It doesn't attack the plus charge because you're going to form the bond between carbon and bromine. You're not going to form the bond between the plus and the minus. Okay, those are just charges. So what do I get then? Well, then I will get as my final product a CHBr. And guess what? I started with 1, 2. I started with 2 different molecules. I ended up with just 1 molecule. What did we talk earlier about addition? Define addition. That's from your O level. Okay? So that's the idea of addition reaction. It's the electrophilic addition. This mechanism is called electrophilic addition mechanism. It applies to addition across the carbon-carbon double bond with an electrophile such as Br2, or I can show you another one now, which is with HBr. Okay? So now I'm going to show you a different example with HBr. Okay? HBr is not like Br2. HBr already has a dipole. The dipole is going to be delta plus on the hydrogen, delta minus on the bromine, because bromine, chlorine, iodine, fluorine, they are all more electronegative than hydrogen. Because of that, you don't really need to polarize the molecule, which is already polar. The same idea again, from the pi bond, from the double bond, because that's the rich electron, attacks the H plus, well, H delta plus, okay? And then heterolytic fission from the bond, not from hydrogen, from the bond, which contain the 2 electrons, it goes to the bromine, okay? So what you're going to get is, again, you're going to get a carbocation intermediate. I add a H, all right? I get this. I talked earlier about what if you don't add the H here, what if it adds there? Because possible, right? The H can go here or the H can go there. Why don't I draw the other one? Where the H go to the right carbon. Then this gives you a plus charge on the left carbon. Are they the same? That's what you're asking. Are they the same? I tell you, they are the same. CH3, CH2 plus. You read from the right to the left, CH3, CH2 plus. They are exactly the same. So this is an example where it's nice and simple because the carbocation intermediates, both are primary carbocation intermediate, because the positive charge on the carbon with the positive charge is bonded to one other carbon, the carbon with the positive charge is bonded to one other carbon, both are carbocation intermediate. I keep on talking about this word intermediate because if you draw a reaction profile diagram, you will have progress of reaction, or reaction progress, or extent of reaction, and then energy there. Assuming, I don't know whether this is exo or endo, yeah? I'm going to assume, okay? So pardon me if I get this wrong, but I will assume it's exothermic, okay? So meaning to say, I will get the reactant there. I have 2 reactants, and then I have 1 product because it's an addition reaction, right? So the other thing that gets kicked out is Br minus. I have to show a lone pair because heterolytic fission. When you break it, it gains the 2 electrons in the covalent bond. It gets the 2 electrons in the covalent bond because this covalent bond is not being split equally. It's an unequal breaking of the covalent bond. Unequal meaning both the electrons go to only one of the atoms. Definition of heterolytic fission required in AS chemistry. Whatever syllabus you're doing, you need to know that definition, yeah? What do we mean by intermediate? Before you do organic chemistry, you will have done this in energetics, which is enthalpy changes. This is your intermediate. When you have an intermediate in a reaction, you will have what we call, well, we don't call it, but I call it. It looks like McDonald's. Okay, this is what I call the double hump. Okay, this is not a technical term, yeah? This is not the correct term. This is my term. When you see this double hump in a reaction profile diagram, it tells you there's an intermediate. It proceeds via this thing which exists as an intermediate. That's why it proceeds via this stable intermediate, carbocation intermediate, and it goes to the product. Okay, so they like to ask in MCQ question, for example, right? Which one of the following reactions fit this energy profile diagram? Well, if it is electrophilic addition mechanism based on the functional group and the reactants that get involved in it, then you know it's electrophilic addition mechanism, then you know it's carbocation intermediate, then you know it's double hump. Okay, please don't use double hump in the actual explanation. Basically, it proceeds via intermediate. Yeah, there are 2 steps. Step 1, step 2. Step 1, step 2, which we are going to do now. From the rich in electron, nope, you don't want to draw straight line. Yeah? You want to draw like a curly arrow. It attacks the carbon. Again, I emphasize it's not from the negative to the plus. Okay, yes, negative species get attracted to the positive species, but your electrons flow from the electron flow is showing you what bonds are you forming. Here you are forming carbon-hydrogen bond. You are forming carbon-hydrogen bond. You are forming carbon-hydrogen bond. Here you are forming bromine-carbon bond. So the electrons is flowing from the lone pair to the carbon because that is the bond that you are forming. Okay, so that is the product. 2 of them come together to give you this product. It's a reaction of alkene with electrophile. It's called electrophilic addition. alkenes undergo addition reaction because it's got the carbon-carbon double bond, one of which is the pi bond. The pi bond contains the pi electrons, like that, okay, which are rich in electrons, and they are the one that enable you to attack electrophiles like this and proceed via carbocation intermediate, which of course the delta plus atom can go to either of the two carbon atoms. Here they are the same carbocation because they are the exact same intermediate, so there's no difference at all. Therefore both of them will give you the same product, which is just bromoethane. Alright, this is electrophilic addition mechanism. I'll cover in a separate video what happened when it's not the same. Alright, so there is your Markovnikov rule. I'll cover in another video. So yeah, please subscribe to the channel and I'll see you in the next video. Thank you for watching.